Okay.
Handshake.
Hey
Yeah.
everyone. Welcome to episode 6 of Robo Papers. I'm very glad today to have Hao Shu with us
Good.
today, talking about his paper AnyDex Grasp, General Dexterous Grasping for Different Hands with Human Level Learning Efficiency. So thank you so much for showing up, Hao Shu.
Yeah.
Maybe as a
Thanks for
start, you
inviting.
can tell us a little bit about yourself. How do you get to where you are today, and give some background about the paper?
Yeah. So hi, I'm Hao Shu, and currently I'm a postdoc at MIT working with Phuket Agrawal and Edward Adelson. So my research focused a lot on robotic grasping and manipulation. And the paper, like AnyDex Grasp, it was a paper that I did during my PhD at Shanghai Jiao Tong University. So it was like a long time ago, actually.
Got it. Cool.
Yeah.
But still very, very fascinating result. And obviously, the paper just came out recently.
Yeah, the paper just came out recently.
Yeah. So maybe if you can give us some background, maybe some prior work that you did, that lead up to
Yeah,
that
so
paper.
previously, like, there are two prior works of
Hmm.
index grasp. One is GraspNet 1 billion. So it's like a general grasping data set that
Hmm.
has like that has over 1 billion labels, and it has like about 40 training objects, and also consisting of 256 like scenarios. And another prior work is AnyGrasp. So it's like a general grasping library for parallel jaw gripper, and it has been used as like grasping foundation models in many projects. And
So
now
just
like
on the what,
yep.
just on that 1 billion set, right? What kind of labelings are you talking about?
So for GraspNet 1 billion, basically we were labeling like parallel jaw grasp poses, and the idea
Hmm.
is like given a scenario like a single view point cloud. So
Hmm.
like we can sample many different 60 poses in the scene. So for each 60 pose, what's the grasp quality? So what we labeled is like the grasp quality score and grasping width of like each grasp pose.
Ah, I see. Yeah, I saw you mentioning in this paper as well. Okay, cool. Maybe we can get
Yeah,
into some of the details later on.
yeah.
Maybe this is a good time for you if you can share your screen, and then
Yeah.
you can give us a quick overview.
Yeah. So basically, like any desk grasp, so what we achieve is like, so the goal is to enable, or the question should be like, so after we enable the robotic grasping for parallel jaw gripper, so
Mhm.
we are happy with that. But the problem is, so nowadays there are so many startups working in this area. So basically every week we could probably see another new hand. And how can we enable like so many different hands to have pretty robust vision guided grasping ability? And one very intuitive way is like, well, we can label data set for each of the hand and then train a neural network for them. But the problem becomes like it's very tedious to do so. So it basically took us several months to label a data set and then train a neural network just for parallel jaw gripper. So it'll be even harder if we want to annotate labels for like a dexterous hand. And based on that, so we start to think how we can solve like grasping problem for different dexterous hand. And the way we come up with like we say probably we can utilize the prior knowledge from existing like uh data set like GraspNet 1 billion, since we already label a lot of contact position and normals. So based on that knowledge, we can first train some representation model and then like train grasp decision model for each hand based on like a general representation. So that's like the general idea behind it. And what we achieve is like, so now we can just train a representation model, a very like general representation model for any kinds of hand. And then based on that, like for each hand, we just need hundreds to thousands of trial and error in the real world, which takes about 4 to 8 hours like real world data collection time. And then we can enable different hands to achieve like pretty robust grasping ability. So that's like the general or the background of this paper.
Yeah, so I understand that you approach this basically in kind of two different stages, right? So firstly, you have some kind of like uniform model that got
Yeah.
overall representation.
Before you get started, how many hands did you end up testing it on? Could you just kind of
So
show
yeah, we
us?
ended up
Yeah.
testing the algorithm on 3 different hands, like a 3 finger hand, 4 finger hand, and 5 finger hand.
And
Yeah.
yeah, so you see good performance on all these different hands. Do you
Yeah.
see? Do you think that? And does the same principle apply to 2 finger hands, or presumably to more fingers, if that was a thing? You think is just generally works for any hand geometry?
Yeah. So in general, I think it works for hand. that grasp the object based on friction instead of like. So there are some other hands that like use suction cup. So our model does not apply on those scenarios. But like if the hands grasp an object based on friction model, then I think basically our principle can be applied on those hands.
Did you notice any major differences in performance between the different like the sizes, the
Yes.
types of, yeah?
So very interesting observation is that the performance actually does not increase when we increase the degrees of freedom of the hand. So like for a 3-finger hand, it basically has 2 degrees of freedom. And then the performance can achieve around like 90 to 97% of success rate in terms of grasping. But then when we increase the number of the number of degrees of freedom to like 6, where we have a like 5-finger hand, the performance degrade to about like 85%. And then
Interesting.
if we try to increase the like degrees of freedom to 16, where we have the allegor hand, it has 4 fingers, the performance further degrade to like 80% or even 75%.
So this is all with the 4 hours of training, right? So this is holding the training of data constant. You're saying that the extra so this is interesting. Maybe we should go into how the thing works before pushing much further on it. What do you think, Michael? Yeah, that's
Yeah,
because I think there's a lot to talk about there. That's really interesting, actually. Yeah, but so do you want to tell us a little bit about how it works?
Yeah. So basically the idea of how it works is like, so if we look at the force closure matrix, so I don't have that matrix here, but one interesting observation we have is like there are actually 2 kinds of information involved in grasping. The first kind of information, they relates more to like the visual appearance of the object, let's say the contact position and the normals, where they relate to the grasp matrix and like the normal or the direction of the friction cone. And there's another kind of information which are like the force vector you applied and the friction coefficient. And those kind of information, basically you cannot extract them from visual observation, let's say point cloud. They can only be obtained during like interaction. So that's like the motivation that motivates us to decouple the learning pipeline into like 2 phases. So the first step, we first learn a general representation model where we take point cloud as input. And then the output would be some contact-centric grasp representation. And they basically contains like positions and normal information at every possible grasp poses. And then based on such low, and I have to mention that such representation, they are pretty low dimensional. So basically based on such low dimensional representation, we can then freeze this model and use that representation to train like a grasp decision model. And such training, they basically, all the training data, they are based on real world trial and error. And for both of these 2 steps, the total amount of training object is just 40. So that's another very interesting observation where we can talk more later. And but the outcome is that grasping algorithm, they're able to generalize to hundreds of unseen objects. So basically, like that's the overall pipeline of our paradigm.
So a couple things to note here. So for this, not so much for you guys, of course, but like, so this is open loop grasping, right? Like I predict a final coordinate, a final position and configuration, move to that, then close it. And so that presumably means like you can train much faster in the real world, right? That's why 4 hours of data actually goes pretty far for you, right? And also you're using point clouds.
Yeah.
Could you comment a little bit on why you made those decisions?
Yeah, because actually,
like camera, right? Yeah, sorry, that's the.
Yeah, so actually, because the main reason is actually because for grasping, it actually basically relies on the geometry, and it actually does not relate to, for example, the color of the object. So that's why we prefer like a single view point cloud, which contains most of the geometry information, although it's not perfect. Yeah.
So this is a single viewpoint cloud. So it's not like you have a perfect view of all the robots. This could be mounted on a robot and just scanned from one direction. Yeah.
Exactly. That's in order to make it more practical, we use like a single view RGBD camera.
So that means you still have issues with occlusion since you you can't necessarily see what is behind. But despite that, it's able to excuse me, have a decent representation.
Yeah, so that's interesting point. So like we don't have the full view of the scene. It means occlusion will definitely like affect the performance. But the thing is, like in most cases, since for this project, it's not object-oriented grasping. It means that the algorithm will just give some like good grasp poses across the whole scene. So like in practice, in most cases, it will just try to grasp the object on top of the, for example, the clusters. So usually those objects, they are not heavily occluded.
But also you can usually use like segmentation methods to pull out the object. With this kind of stuff, you can
Yeah,
usually use
if you want.
segmentation to pull out the one you specifically want. But
Yeah.
like if it's blocks, you might as well get something out of the way first and then get a new image, right?
Yeah.
That's
Exactly. So the good thing is like, or the philosophy behind any grasp and any DEX grasp is like, we want to decouple the object segmentation and grasping, the semantics part and the geometry part. Yeah.
makes a lot of sense. This kind of thing it's really nice because it means that you can, like, when something new comes out, like a new foundation model like Gemini or whatever that can help with the segmentation part, you can just immediately get that advantage right into your
Yeah.
method. Yeah.
Exactly.
Yeah, I guess I mean, so I understand about the representation model, but could you talk a little bit about how does that represent? I mean, how does the first step then lead into that training for the decision model?
Yeah. So okay, maybe I can phrase it in this way. So one reason that previous end-to-end model, one reason that they require a lot of training data is because they need to learn the mapping from raw point cloud to the final graph success or not. And such mapping is pretty non-linear, or is highly non-linear. And it means that they need a lot of training data for that. But if we start from like some low dimensional representation, which only contains contact position and normals, like in this figure, for example, given an object, the way we encode is we first like slice the object along the approach vector direction. And then we got multiple tangential plane. And on each plane, like we'll discrete the whole plane into like, for example, 48 beans. And each bean will obtain its normals and grasp point position. So it means that for each object, when it comes to grasping, it can compress the geometry information into just hundreds of bits, or like just how should I phrase that? So in total, for a grasp pose, the local geometry will be compressed into 480 parameters, which is pretty low dimensional. And we just need to learn the mapping from 480 parameters to whether it's grasp success or not. And such learning just require pretty much less like training samples. And basically such learning is even easier than training a neural network to classify on MNIST dataset, right? Because the input is just so like low dimensional, maybe even lower than the MNIST classification problem.
So I guess what you're saying is that from these point clouds and then changing into this contour and then along with the normals, the perpendicular line basically coming from the surface,
Yes.
it's a very small it's a very small size representation, and yet it's accurate enough to I see.
Yeah.
So I suppose at inference, all this the calculation is super quick.
Yeah, exactly. So during inference, like for each trial, we need to first run the representation model. And then after we get the representation, we sample a 60 pose, or actually we sample like thousands of 60 pose and get representation for all of these poses. And then we run the classified neural networks. But the classified networks, or we call it grasp decision model, it just has 7 layers in total. So it's a very tiny networks, and it can be run extremely fast.
So sorry, when you say 60 poses, what do you mean 60 poses? Like
Oh,
you
60 poses basically means we sample different positions and orientations
Mhm.
in the scene. So 60, that means 3 translation and 3 rotation.
Do you need to sample configurations as well for the fingers?
Oh yeah,
Or, yeah.
that's another thing we sample, like the configuration of the hand.
So this means that do you find yourself needing to do much search, like cross entropy optimization or something, to be able to find the actual correct or best grasp pose? Or
Yeah, so actually, in theory, after we have all the possible contact positions and normals, we can actually run some optimization algorithm to get a good grasp pose in terms of like configuration. But to make it easy, we just say, let's just sample thousands of poses and then sample like all different possible kinematic configuration of the hand and just classify them. And it just makes the pipeline easier so that we don't need to run the optimization algorithm.
So I guess a big thing that you were saying about this study is that how it only went from, I say, 40 different objects during training, and yet it's
Yeah.
able to start handling more than 100 unseen
Yeah.
objects.
So that's
How close are those like unseen objects compared to those 40?
so
Are there
they
some
could
very
be
different ones?
yeah, they could be actually very different. So here I think I got a figure in my paper. Hold on. Yep, so this figure it shows our training set and the test set. So basically, our test set will also include deformable objects like snacks and this kind of fabrics, clothes, and it also contains adversarial objects from like EGOT and DexNet. So they're actually pretty different from our training set.
and you did not train on deformable objects, right? You
No,
don't.
we didn't train on deformable objects, but we observed that the test performance is actually even better than rigid object because the deformable object could comply to the gripper when it like.
Yeah, I would actually imagine if you trained on deformable objects, it might hurt performance because it would be expecting that it could deform, right? Yeah.
Yeah.
That makes sense.
Could you comment about, like, earlier on you say, and this might be something defined in your earlier work, where you had some concept of grasp quality?
Yeah.
How do you quantify something like that? Yeah.
So for grasp quality, basically, there are 2 ways of classifying them. One way is like if we have the CAD model of the object, we can actually run force closure metrics. So there are actually some existing model, like people from mechanical engineering, they might work, they have worked in this area for decades, and there are many good mathematical model, like grasp range model or like force closure metrics. So the idea is like given a full CAD of the object and a 60 pose, it can just directly compute the grasp quality of such 60 pose. And you also need the grasp configuration of the hand. Yeah. That's one way. Another way is you directly like evaluate the grasp poses in real world by try and error, and you just classify whether it's success or not.
So I think in your case you went with the try and error, right? Like how do you, could you go through the setup a little bit?
Yeah. So try and error. So actually, how should I phrase it? So the thing is, when we were training the grasp representation model, the data comes from GraspNet 1 billion dataset. So we basically re-annotate GraspNet 1 billion so that it contains possible contact position and normal pairs at different 60 poses. And then like for the grasp decision model, the grasp quality is just like for each trial whether it's success or not. And then we just train a neural network to classify like for each grasp. And given the low dimensional state representation and the grasp configuration of the hand, whether it will end up being success or not. So it's just like a binary classification problem. Yeah. It actually did not output like the quality score. It just tried to output the binary score.
And for each time, how many times do you try with each object?
So let me think. We actually have different size of training set in our ablation study. So at first, try to train like for each grasp configuration, we try to collect 1,000 like try and error sample, and then we gradually reduce that number to 100 and then 50. So like we do not count the number that we tried on each object, but we count the number that we try for each grasp configuration or hand configuration. And the number will vary from 1,000 to 100 and then 50.
So what's the rationale of dropping that again?
No, the reason of dropping that is just we try to see how efficient can we learn grasping. Like after we successfully learn grasping with 1,000 try and error samples, we try to find the lower bound or the minimum number we need to successfully learn grasping. That's also something interests me a lot. Because like for us human, we probably don't have the chance to train on thousands of objects with like billions of labels. Then I try to ask myself what's the lower bound or how efficient can we learn grasping? That's why I reduce the number of training objects and also the number of try and error in our experiments.
Do you think pre-training could help with that though? Because like, so you trained on 3 robots, right? If I want to train on a 4th robot, presumably I could. Maybe there might be. I mean, not with this particular setup, but maybe there's a way of tweaking it so that you can train on those 3, all the data you have from those 3, and then get the next one with just a dozen samples or something.
Yeah, I think so. There are 2 paradigms. One is like if we train the grasping in an end-to-end manner, like let's say we train one network for different hands. So in that way, I believe that we can definitely benefit from training data collected by other hands. But in our paradigm, we actually implicitly did that because we first learn a representation model. And this representation model basically contains all possible contact positions and normals. And you can regard that as like you have many different kinds of hand and you already have like billions of samples.
Yeah. So you don't think there's extra value, I guess, to the real world data that you've collected to fit for the particular hands then?
Yeah, actually, that's a great point. We haven't tried that yet. So maybe, actually, not really. So in this paper, we train like different grasp decision model for different hand configuration. And we found that when we try to train one single networks for different hand configuration, for example, it's 4-finger hand, but it has different kinematic configuration. And if we try to train all these configuration within one network, the performance actually degrade a little bit.
Yeah.
Yep.
Yeah. That
So
makes sense.
maybe does not help too much in this case.
Yeah. I mean, particularly since you would need to presumably have some parameterization for what the gripper was actually to be able to get some generalization, and that becomes there's a whole fairly large input space that needs to be added, right? Which also would mean you'd need lots of support for that in your data. That makes sense. Yeah.
Exactly.
Yeah.
Yeah, and maybe we can go back to earlier on when you guys were saying about the different fingers, right? I think you have a figure 2 where I find it quite interesting that some of the ways that the fingers will go about grabbing stuff,
Oh, let me see.
there's a lateral one where it's like a 2-finger. So I find it quite interesting.
Yeah.
Any learnings from these?
Yeah, so basically the idea was for human grasping, we actually have some grasp taxonomy, and it has been studied for decades, especially from the paper of Mark Katkowski. And it motivates us to like also discrete the grasp poses or configuration of different hands into a limited set. That actually decrease the number of or the space of our configuration, or actually that decrease the configuration space, but also allows our grasping to have enough variance to support like subsequent manipulations. Because if you look at grasping paper that use reinforcement learning, in most cases, when they grasp object, they use a power grasp, which means they use all their fingers because the only optimization goal for those reinforcement learning is the grasp success. So if you use a power grasp, then you can have pretty high success rate, but then you cannot have pretty good ability to support subsequent manipulation. And that's why we try to discretize the grasp space or the configuration space so that we can have both pretty high success rate while also have enough configuration to support subsequent manipulation.
How do you gauge the subsequent manipulation? I mean, in your case, the try and error is only graphs and that's it, right?
Yeah.
In your paper,
But imagine like we can actually use it as a module to support like in-hand reorientation. For example, nowadays, all in-hand manipulation paper, they just show that, or they have an initial condition where the object is in their hand. But none of them show that we can actually do the full manipulation process, like grasp an object, reorient it, and then use it to, for example, do some task like assembly. So if we provide some good grasp poses, then we can use this module as the first step. Like we grasp an object, and then we do some in-hand reorientation, and then we do some like actual task like assembly. So that's the idea behind it.
got it. Yeah.
Yeah, but actually there's one thing I wanna mention, which is we can go back to the 40 training object things, which is something I found really interesting. So let me go to that figure. Yeah. So one thing we observe is like when we were training the AnyGrasp, which is a prior work of this project, we just use 40 training objects, but we don't understand why like just train on 40 objects could give us such good performance. And we start to investigate that problem here. And we realize, one thing we realize is actually for grasping, a good data set means we should have more diverse local geometries within the gripper. And it actually does not mean we need more training objects, because if we look at human, when we were young, we actually don't have the chance to play around like thousands of training objects. We just would have like hundreds of toys, for example. But for each object, we will spend a lot of time like playing around with it. We'll even bite it. And that means we are actively exploring every potential local geometry on that object. Then we start to ask one question, which is if now we have 2 dimensions to scale our dataset. One dimension is the number of training objects. Another dimension is like how dense we sample local geometries on each training object. So after we run such analysis, we found that when we increase the number of training objects, diversity of local geometries that we can have actually does not increase a lot. But when we increase the number of sampled local geometries on each training object, like diversity of local geometries increase dramatically. So that actually motivates us to just have a training set with limited amount of training objects, like 40, but we will really densely sample on those training objects. And such motivation, observation allows us to like curate a small data set in terms of number of training objects, but it can really generalize well to hundreds of unseen test objects.
Yeah, this is actually a really nice, really interesting result. I think it's
Yeah.
a big advantage of presumably of your model operating in 3D, right? As well, because it'd be very hard to get this kind of result if you were just doing end-to-end learning from cameras, right?
Yeah,
Like,
exactly.
Nice. Yeah.
And so sorry, so when you say you sample a lot more for each object,
Yeah.
do you mean you just place it in different like orientation, position, and then you try? Is that what you mean by sample? Different sample?
Oh no, it means like, so when we were building the GraphNet 1 billion dataset, it means we are actually densely sample 60 poses on each object. And then if we project those 60 poses onto the scene, it means we have pretty dense 60 poses in the scene, like at many different locations. Yeah.
Got it. I see.
So to give you a number, basically we sample over 20 million grasp poses on each training object. So that's extremely dense.
I'm surprised actually that this doesn't matter more for like the higher degree of freedom hands, because like they can presumably contact lots of different places on the object. So that means that doesn't the combined geometry, like there's a variation that increases when it comes to like the combined geometry of all the places the fingers are touching, right? Or is it just like one contact and that's why you can kind of scale this? So
yeah, that's I think that's a great question. So when we were conducting the analysis, we were using local geometries within a parallel GeoGripper, so as shown in this figure.
Mhm.
But the good thing of any DEX grasp is like we first train a representation model. And such representation model, when we are predicting the contact positions and normals, like even though we are predicting like multiple contact positions and normals, each prediction, they are independent from each other. So it means that when the local geometries of this kind of geometry enclosed by a parallel GeoGripper, although they might not, the conclusion might not hold if we have sample a different shape of the local geometry. Since we predict each contact positions and normals independently, it does not affect our conclusion that increase the number of training samples on each object would just increase the diversity of local geometries.
Do you think that if you were doing pre-training with pre-grasps for dexterous hands or something, you would see different results?
Pre-training with dexterous hand.
Right. I'm not sure how you do it, right? But like hypothetically, if you could pre-train, if you could do this if you had like 1 million dexterous grasps and we're pre-training your encoder that way, do you think you'd see different results?
I think it would be pretty similar actually.
Okay.
So like you mean pre-train our representation model, not with
Yeah.
the
Yeah.
contact representation, but with like
Because the local geometry can then capture like the interactions between like multiple fingers, I guess.
Yes.
Or like the concept of locality is different, I guess, here.
Yeah, I think that's definitely possible because if we train our neural networks for a specific hand, then basically a neural network will encode two kinds of information, I guess. One information is the geometry related information and another would be like graph decision making information. So yeah, I think the first part of such information will definitely help in terms of like transfer to different hands. Yeah.
That makes sense.
I also have a question about I think you have this diagram. Let me see, it's figure 6. You have this success rate specifically about allegro grasp posture type.
Yeah.
Could you comment a little bit on a bit? So yeah, for those of you who are listening in, I don't know how to describe it, but basically different ways of it's I think it's a 4-finger hand, I think.
Yeah, 4-finger hand.
But it's but there are obviously many different ways to use those hands to grab the same even the same object. So could you explain a little bit like the spread of the success rate here?
You mean the figure C, right?
Yeah, figure C, exactly. Figure C.
Yeah. So in this figure, we are actually trying to discuss with the number, we call it grasp taxonomy. So would the number of possible grasp configuration affect the overall success rate of grasping? Because as I mentioned, for reinforcement learning, like most of the grasp poses, they are just power grasp.
Power grasp.
Yeah, power grasp means like the grasping involve all hands and also the palm. So in this figure,
So in this figure, we can see that there's 10 different types of grasps, right?
Yep.
Yeah. And there are like 67% of the success rate comes from like a single grasp, which is actually only using 3 of the fingers. So it's not the full grasp you were just describing, right?
Yeah.
And that it's like keeping the index finger pointing out while surrounding a sphere with the other 3 fingers.
Yep.
So that's just basically the preferred or the best type of grasp of the Allegro? Is that yeah.
So the first type of grasp pose is actually the grasp pose that has the highest grasp success rate. Yeah.
Why does it not want to use that index finger? Why is it staying pointing out straight like that?
I guess
Irrelevant.
because that will avoid some collision.
Yeah,
Because
okay.
we select the grasp poses based on grasp or after collision detection.
Gotcha. And then the next 3 of the next 4, let's say, are using basically all the fingers surrounding the object. and one of
Yeah.
them is a distal grasp, so pinching between two fingers, which is
Yeah.
like
Yeah.
scissors, right? Which is a
Yeah,
little
like scissors.
unusual.
But
But that
that's
definitely
kind of
makes
like
sense from
a
the collision
parallel
point of
gripper,
view.
right?
Yeah. Yeah.
In a
Yeah,
way,
that's
two
Like,
finger is
yeah.
a little bit like parallel gripper, maybe.
It also probably
Um,
minimizes collisions with the environment too, because you can get into stuff and grab a fairly narrow patch that way, I would
Yeah.
imagine. Yeah.
Oh, and remember now, like the motivation behind this figure is like for each grasp configuration, they all have different like grasp success rates. So for example, the first one, it has the highest grasp success rate. Then the question becomes like, what if we just do grasping with this one specific grasp configuration and ignore all other grasp poses? Like, can we increase our general grasp success rate? And we found that it actually cannot achieve that because, like, for other grasp poses, they were selected for some reason. Maybe like they can avoid more collisions. And if we just use one single grasp poses, it actually decrease the performance. And then the question also becomes like, do we need that much grasp poses? So we found that if we continue to increase the number of grasp configurations, the performance gain we can have is becoming smaller and smaller. So it also makes sense for us to have a limited set of grasp configuration such that we can achieve both high success rate and also it decrease the difficulty of learning or makes learning much more efficient.
Yeah, this is a nice argument for
Yeah.
having for dexterous hands for all kinds of tasks though, because it does say like if I only had like the very simple like pinch grasp essentially, like it would not be able to succeed in some cases. Although I'm really curious because the one that adds the final one, which adds only 2% or 3% performance, is
Yeah.
like this very strange grasp where you have a fist and you pinch something around with your thumb, and it is hard to imagine when that could come up and nothing else would work.
Yeah. Oh, actually, the
it's
last
a
slide.
combination of 5, right? Or
Yeah,
of
it's
5 of those.
Yeah, it's
Yeah.
Oh, it's
actually
all
like
5 of them. Okay. Sorry. Yeah, you're right. Yeah. So, okay.
So-
Yeah.
Yeah, it's interesting. Yeah, it's like I don't know whether Chris, whether you use chopsticks. I'm sure you use, but you
Yeah,
know,
yeah.
once there are all kinds of ways to use a chopstick. By the way, once you get used to one, I mean, the way I hold my chopsticks are pretty like my parents scold me all the time. This is not the way you use a chopstick since young, but it works for me, and I just stick to it. Probably not super high success rate, maybe but it's good enough for. But I guess what he's trying to argue here is that maybe you just need a couple of these variations and that could cover most of the bases. And
Yeah, that's the main argument.
interesting. But I mean that going back to you there are some of this success rate that was very, very high. I read somewhere that it's what's that? I think 90 something percent. Did I make a mistake?
7%. That's for the three-finger hand.
3-finger hand.
Yeah.
And sorry, so this 97% is across all like 150 unseen objects, or
Yes,
Um,
across all 150. And yeah, we just found that the grasp performance on adversarial objects and on like daily objects, they are pretty similar.
So I did have a question about that from the very beginning.
Yeah.
I would like to, so if I can jump in. You're holding two parameters constant across these grippers. One of them is the 4 hours of training data. The other one is the amount of optimization, like the amount of samples that you're drawing. So it would make sense to me if is this a fundamental problem with those grippers, or is it just that relationship breaks? Like, so basically we know that with every extra degree of freedom, we need more data and more samples to get the same performance. Is that the actual, is that the lesson, or what do you think of that?
That might be the problem. Like what we try to keep constant is the total amount of training samples. So it's actually not the real world training hours.
Mhm.
And
Oh, okay.
yeah.
But either
So-
way, actually, I think it still applies, right? It's if it's the same number of training samples, so like
Not really.
Yeah.
For example,
okay,
when we used the allegory hand, it actually took longer because the hand sometimes it will break or
yeah,
it just moves slower.
yeah, the Allegro hands do break a lot. No,
Yeah.
that's big. But I guess if it's if it's one sample, but I guess there's this ratio of like degrees of freedom to amount of data, right? And the point is that is actually going down as you progress in number of fingers, it sounds like. Partly because it is harder to collect data with more fingers, partly because it's harder to sample with more fingers when you're actually trying to test it, because like there's more configurations you can sample from, right? Presumably.
Oh, yes.
Yeah. Or is that not? Or I'm misunderstanding something there.
Oh, not really. So for the sample, we collect, for example, 1,000 samples for each grasp posture.
Okay. Oh, right. Because you actually have a fixed list of grasp paths. So so that is actually constant. Okay, that makes sense.
Yeah, that's actually constant.
Okay.
So I think main reason that when we increase the degrees of freedom, but the performance degrade is because we don't actually have good tactile information or like force torque information. Like our neural network does not.
But why does that not matter as much for the 3-finger or 2-finger grippers, which also presumably don't have good tactile information?
Yeah. So like one assumption I have is like for hands with lower degrees of freedom, like tactile is not that important. But when we increase the degrees of freedom, tactile is becoming more and more important.
Why?
Yeah, because for higher degrees of freedom, since we can move in different ways, and for grasping, we are trying to build context. And during the process of grasping, we'll constantly like old context and build new context. And when the degrees of freedom increase, we have actually more ways to move our hand. So we need more information during the contact. And that's why we need tactile information. But for parallel jaw grasping, since we are always moving in one direction, tactile does not help a lot.
That makes sense.
Well, yeah. So I guess I mean, as a layman just looking at this chart, it seems that maybe 3 fingers are all we need.
Well, it's just for grasping, yes. But for dexterous hand, so there are basically two kinds of advantages. One is that they can achieve slightly more task. For example, parallel jaw gripper. If we have 2 parallel jaw gripper, we can actually achieve 80 to 90% of our daily task. And then if we have a dexterous hand, we can probably achieve like 100% of all the tasks we have. Another is efficiency. Like a dexterous hand can improve the efficiency by a large margin. And for parallel jaw gripper, we might need many additional steps to accomplish the same task.
I see. Efficiency
meaning like time taken to perform a task, right?
Yeah, time taken to.
Interesting. But what you're also arguing here is that if we really want to take advantage of that kind of efficiency, we need touch sensors.
Yeah, definitely. That's something I have been working on in the past year, like dexterous manipulation with good tactile information. Yeah.
Very cool.
Oh, cool. Yeah. Well, look forward to hearing more about that.
Yeah, thanks.
Cool. I mean, I would say for me, like, the reason why I was excited to chat about this with you is the first thing usually I look at this paper I just look at the success rate straight away. Anything more than 90%. I mean, in this case, it was like, close to 100% in some instance. It was really impressive. So really wanted to chat with you about this. What do you think are some of the drawbacks though, like to this approach or limitations? I mean, you mentioned we need touch sensors for higher dexterous hand.
Yeah. So for this kind of method, the first drawback is like it's open loop. So like when the object moves, you cannot actually like adjust the grasp poses. And the second drawback would be like we need to use it with some other module, for example, segmentation module, planning module, to achieve some like meaningful task. So it's not like if we learn this kind of behavior in an end-to-end manner, we can reuse those samples and just collect more data to like achieve good manipulation policy. So for this kind of grasp module, since it just focus on grasping and we just detect the 60 pose, so it's hard to combine with other like manipulation data, for example, foreign peg insertion or other task.
There are advantages to it too, to the modularity. And one of the nice things about methods like this is that you can like filter the area on the mask where you're generating your grasp candidates, right? So like if I know that I need to grab the handle of something and I can detect a handle. So like there are some really nice qualities like that. But yeah, But the open loop thing, if you don't know what open loop is, right? It's like the equivalent of me like looking at this object and then closing my eyes and then executing the grasp, right? So it is actually quite a bit harder than I think than I think the layperson might think, right? That
Yeah.
Yeah, so
anyway,
I suppose
I
in
thought
the
this was
open
really
loop
cool work.
setting,
Big fan. Yeah. Anyway,
effective recovery will be a lot harder, I suppose. Is
Recovery-
that the
Recovery is one issue, and also like you also require like the grasp pose to be very accurate. Like if you accidentally poke the object when you were
Yeah.
grasping, then like the object pose will change, and then it means that your grasp pose might not be as good as before.
it means
Got
you
it.
can't do these really contact-rich grasps, right? Where I'm like pushing on the object in a particular way as I grasp it to get, which is also perhaps a reason why the higher DOF hands aren't doing as well, right?
Yeah.
Well, I guess which is what you were saying earlier with the tactile stuff, right? It's,
Yeah.
Yeah, well, I guess. Yeah, so how should I guess a couple of usual questions we like to end with. It's if let's say if you have 1 or 2 more months to squeeze into this paper,
Yeah.
what were some of the improvement that you will wish to push in the paper?
So like one interesting thing is something we actually so the thing is like as I mentioned, like we got the results in June 2023, but then like I spent maybe 1.5 years trying to figure out something else and polish the paper, right? I come up with the full manuscript. So basically, we did many experiments, but some of them they are not actually included in this paper. One interesting thing is now we show that we can decrease the number of training objects. So in this paper, we show that when we use 140 training objects, and then we use like 40 training objects, like the performance decreased by just a little bit. And then we can actually try to further decrease the training object. So in this paper, we decrease it further to 30, and the performance also actually just decreased a little bit. So one interesting thing would be like using our metrics to measure the diversity of training set. We can actually select a minimal set of training objects, for example, 20, that contains the most diverse local geometries across the like 140 training objects. So in that way, it means we can have a very limited amount of training objects, which can enable very good grasping performance. So that's something maybe not necessarily like the grasping community would be interested, but I think it's very like mentally interesting to me. And I think the researchers in, for example, child development or cognitive science, they might be interested in such kind of research.
Yeah, but I guess because as you mentioned earlier on, like the size of that, of the contour and the normal information,
Yeah.
ends up being so small and yet so high information rich that
Yep.
I imagine even like the cost of having just, let's say, 30 or maybe like you did in this paper, the main thing was 40 objects, right? The cost of having more objects is not super huge as either way, isn't it? When you're doing the actual training.
So it
Or
might.
is there some
because
reason
when-
to really still want to minimize like benefit
Yes.
is there some benefit to finding
Yeah.
like that minimal that you talk about?
Yeah. So technical wise, not really. Maybe I think 40 is good enough to have good performance and have a balance between training effort and the performance. So it's just like I just feel interesting if we can
Got it.
see a even smaller training set. Yeah, to me. But like as you mentioned, like what happened if we increase the total number of training objects in our pipeline? That might actually decrease the performance because when we were annotating the GraspNet 1 billion dataset, we just use 40 training objects and we sample like, for example, over 20 million grasp poses on each training object. But imagine if we increase the number of training objects to, let's say, 1,000 or even 10,000, then the number we can sample, if we want to keep the same computational resources we need, then we need to decrease the grasp poses we sampled on each training object. So that would hurt the performance.
So this comes down to that trade-off mentioned earlier, where the denser that you sample, the more more unique patches, local patches you get. And that is like the fact that most rigid objects are actually not that different on a local level. So sampling
Yeah.
more densely is more valuable than sampling sparsely on a very diverse set of objects, because you'd get less diversity that way, right?
Yeah. Yep.
That's a very valuable takeaway, a very interesting takeaway. I think.
I find it very interesting.
Makes a lot of intuitive sense too. So it lines up with a lot of things that I've seen. So
Yeah.
Yeah. I guess maybe a final question.
Mhm.
How should are there any like interesting papers that you came across recently that you want to give a shout out for?
To be honest, in the past year, I mainly focused on mechanical engineering.
it can be a robot mechanical engineering paper if you have what's the most interesting thing that you've seen recently?
There's an old paper, but it might be too old. It's from 26.
Oh wow. What's that paper?
Let me try to see if I can still find it somewhere. Oh, it's called Washington Hand.
Okay, you got me intrigued, man. Usually everyone is recommending something that's like fresh out of the oven.
Oh, this one.
Cool. Oh, that's a really interesting hand, actually.
Yeah, basically it's the hand with highest degrees of freedom so far. And it basically replicates every joint of humans.
Very cool.
On the hands.
But it's a long time ago, 2016.
Very cool.
Oh.
Yeah.
What happened to this? I guess they
think-
abandoned.
No, I think it's just mechanically too complicated, so they didn't follow up the design, which is a
What's
bit.
this called? This is called Washington Hand. Okay, cool.
Okay,
You know,
just
looks
call it
very-
Washington.
Chris, have you seen this before?
Actually, I don't think so. I think I must have, but no, that's very cool.
Yeah. They have the video.
This is from 2015, you see? 2016.
16. Yeah.
It is
9 years ago.
like
Wow.
you see these very cool demos from the humanoid companies these days, like the Tesla hand. I was like, oh, this is certainly a better hand.
Yeah.
No, but check out the sensor that this guy has
Yeah.
got his
Yeah, that part
arm
is,
at.
yeah, he
That
got his
part
whole
is
arm
incredible.
encased. Yeah, it's incredibly low.
No,
Yeah,
but this
that's
is
amazing.
really dexterous. Oh wow.
Yeah,
This is okay. I
Full
see
human
why you are
dexterity,
intrigued.
You actually even
Ah.
replicate the bones of the human hand. Like, that's crazy.
yeah, bones and tendons and everything. Incredible.
Yeah.
I'm
must be very
equally
compliant
intrigued.
compared to a normal robot hand.
Oh wow,
Yeah.
wow! This guy's squeezing CDs. I'm equally intrigued by the teleoperation technique. The bunch of things you see on the guy's arm.
That's quite impressive right there at putting the pen.
Wow.
All of this is.
How is he doing all this? Man, I mean, how is he like teleoperating this? Okay, this is very interesting. So
Oh.
really using mechanical, well, okay, interesting. Not like
Yeah.
all this like VR stuff, right? Just do the mechanical. Interesting. Okay. Wow.
that's
Thanks for
amazing.
sharing that. That's very cool.
Uh-huh.
Yeah.
Yeah.
Uh,
You're welcome.
and
Yeah,
thanks for coming on.
yeah,
Thanks
we'll
for-
make sure.
yeah.
Yeah.
Thanks for taking time.
I
Yeah.
think really fascinating research.
you.
I'm glad you managed to, got the paper out and share it with the world.
Yeah, thank you.
Yeah. Thanks for coming on.
All right.
All right, Chris. What have
Hey.
you learned?
Cool. This was a really cool paper about AnyGrasp, about grasping objects with dexterous hands and training like open loop grasping methods that work for a wide variety of objects. And there's a lot of cool information there about like training and what made training valuable for dexterous hands, and what's useful to have, what qualities are useful to have, and how to get diverse data and what diverse data means in this context, stuff like that. It's cool to see. I really liked the fact. So that one interesting result is that the 3-finger hand was generally better than the full 5-finger humanoid hand, which is
I find that I don't know whether it's the right analogy. Is a little bit like maybe in the self-driving domain where, adding LiDAR on top of vision, it sounds like you adding more sensing ability or more ability, but then the fusion part is the part that usually throws you off. It's like too much capabilities. Like how do you deal with that? Uh, um, yeah, I mean, from what he said, it sounds like he believes that like if you were to go beyond 3 fingers, we probably need to start to require like decent touch sensors, like basically force feedback.
Yeah, it's like because the multi-finger grasps are more contact rich actually. So this was one of the things that we discussed, which I think is interesting, is that like because you need the tactile sensor probably right. To do this, when you grab something with more fingers, you're making lots more contact and being much more reactive. And like because of the way this type of method is set up, like this type of method has a ton of advantages when it comes to like leveraging open source or leveraging VLMs and leveraging like it's modular, which makes it easier to train and deploy and lower cost and faster and all these other nice qualities, but like and more reliable but also it means that it's not closed loop, which means that you can't do all this nice reactivity to tactile sensing that we as humans do when we grasp stuff, right? So like it's yeah, there's a lot there. It's interesting, I think.
Yeah, I think the other thing also, like, I don't know whether it's the right way to think about it, but because he basically used a point cloud for this, right? So presumably, if you have the fourth and fifth finger, chances are the things that you're picking up, the contact point of those fourth and fifth finger are usually occluded, I suppose, by the object itself. Would you say so?
Well, but that doesn't matter actually, because like because it's all open loop. So like it's like taking a snapshot and then close, right? So so there's no occlusions, but there's also no updates, right? So yeah, it's
sure.
Yeah, it's just the fundamental problem with this, with the fundamental limitation. I wouldn't say because it is actually, again, like these do work quite well. I think the big downside of doing this open loop is actually what he was saying was efficiency, right? Like, so because I may have to retry 3 times to get it to work, but it will probably, but I can get really high accuracy with methods like this. And it's because, but it's also like limited in the types of grasp, because I'm not going to do a grasp where like let's say I'm grabbing a book from my bookshelf. I'm going to reach out and like pull it with a finger and then close around it. And that's the kind of thing that these open loop methods can never do, right? That being said, most tasks you can do open loop, right? Like, so there's it's a nice method. And the 3D element, I think I'm a big fan of adding in 3D structure to stuff like this. I think that it really improves reliability. Like the analog to kids, right, when they're learning to grasp, they definitely don't, like you pointed out, right, they don't grab that many different types of objects, and they get a pretty robust grasping system going without really grabbing like hundreds of thousands of objects. So you can get pretty good off of just a handful of objects grabbed over and over again, right? Well,
I suspect. I don't know. I mean, but for kids, I mean, they don't have so-called 3D, right? I mean,
they don't, but
they
do.
They have stereoscopic.
We have we have stereo vision and do some amount of like internal. There's tactile. Yeah, there's a lot of stuff going on different there. Yeah, but like yeah.
Okay, well, interesting paper. I think it's interesting that the previous week was also also used 3D, right? Or actually also used point cloud, and got really good results. So yeah, to your point, I think maybe more researchers should put a depth sensor somewhere.
Yes. They really are like a nice shortcut. I think they really allow. I think they particularly allow you to deploy stuff quickly with smaller group teams, I think, compared to vision, because like for a lot of the pure vision methods, you need just such huge amounts of data, and you need really good support for everything. Whereas the 3D stuff builds in structural priors that make generalization much easier, right? So like, I think how there's a very large there's a whole discussion you can have about about the analogs to humans. Like, I tend to come down on the side that humans have like we have very modular. We actually have a fairly modular vision stack, right? Like, it's just that it is all end to end, and so like, right, it's all end to end, but right, because like there's high specialization in different components of the brain, right? But like at that point, like in the end, robots are just different, and who knows what the right answer is? But I don't know.
All right, cool. Sounds good.
This was a lot of fun.
We'll do it again, man.
Yeah. See ya.
Okay.